Hi, thank you for watching my presentation. I'm excited to share with you a permafrost terrain classification framework I've been working on that aims to unify how we classify permafrost terrain across regions, disciplines, and scales. The title hints at this, going beyond just calling it frozen ground, bringing a more integrated perspective on permafrost terrain, and paving a path forward for unifying practices in the permafrost science community. Some of you may have seen me giving talks about this before, as this is an ongoing project. But don't worry, I have plenty of new stuff to show. Let me start with telling you what I will talk about in this presentation. First, I will briefly explain why permafrost terrain classification is such an essential tool. Then I will explain why we need a framework. I'll then discuss the core principles of the framework, and then walk through some classification examples showcasing the framework. By the end of this presentation, I hope to have given you a clear sense of how this new permafrost classification framework can not only bring more consistency to how we classify and compare terrain, but also improve model integration, support prediction, and help us synthesize fragmented knowledge across regions and disciplines, while staying grounded in field observations. Oh, and this is me, by the way. I am Niek Speetjens. I did my PhD in Arctic hydrology and biogeochemistry at VU Amsterdam, focusing on lateral carbon dynamics in permafrost regions, and I was drawn to my current postdoc position at the University of Victoria, working with Professor Lance and Professor Gruber, because it aims to solve a profound problem in permafrost science, one that I ran into during the final stages of my PhD. This is the key figure of the last paper I wrote for my PhD dissertation. It shows the conceptual layout of a model that I built which coupled ground freeze-thaw cycles, surface processes such as snow redistribution, hydrological functioning, and the lateral movement of dissolved organic carbon from the soil into surface runoff for ice wedge polygon terrain in transition from low to high-centered polygons. As you can see, there is quite a lot going on here, and the model needed quite a bit of parameterization. But this can be expected when you are trying to integrate multiple drivers that are all interconnected somehow. And I had been to the field, so parameterizing was not hard to do initially. And using classification, I was able to scale my modeling results to the study area. Done, you'd think. But ambitious as I am, I was not satisfied with just modeling one site. I wanted to know, what does this mean in the greater scheme of things? And this is where I ran into a lot of problems, or questions I should rather say. For example, how representative is my classification at a broader scale? What broader context controls how my site functions? And how is this different in other places? If I want to parameterize my model with data from other sites, how do I know for sure this applies? Did I even consider the right variables? Basically, what is the value of what I am doing here if there is no framework that I can refer to classify my permafrost site and compare it with others, let alone extrapolating findings to a circum-Arctic scale? That would come with huge and unnecessary uncertainty. And my model problem is just one example. Permafrost landscapes are vast, covering about a quarter of the northern hemisphere. They are also immensely diverse and rapidly changing. I am sure that you and others working on permafrost watching this are doing so in very different settings across terrain types that are often labeled the same, like tundra, continuous permafrost, ice wedge polygons, and so forth. When it comes to how we classify permafrost terrain, things are surprisingly ambiguous. And this challenges the comparison between sites, synthesizing of studies, and predictions in space and time. So we need frameworks that help us generalize without oversimplifying. Right now, we are often left choosing between classes that are too coarse to be meaningful, for example, continuous permafrost, or classes that are spot on in local settings but difficult to use at broad scales like PALSA or ice wedge polygon. Would it not be nice if we, as permafrost researchers, could agree on a shared rationale of how we view permafrost landscapes and how we place, for example, field observations within a broader context, allowing us to infer better rules for generalization and communicate uniformly about what distinguishes one site from another in terms of permafrost conditions? Such a framework would allow us to better compare between sites, constrain field variability, synthesize studies, parameterize models, make predictions, communicate results, and ultimately, adapt to change. Currently, there are many classification products out there that you can use to stratify your permafrost research or generalize your findings, but these are often not specific to permafrost, lack integration, and have ambiguous relationships. My goal is to build a framework that connects multiple scales, is process-informed, and usable, whether you're sampling in the field, modeling, or mapping risk. It is about capturing terrain logic, how these landscapes formed, what controls their current state, and what makes them vulnerable to change. Ultimately, this framework is a tool to help us speak a shared language across sites, disciplines, and data sets. To develop a common framework, I dove into literature and distilled 3 core principles that hold true for most of permafrost science and formulated them into a short reminder, which I call the ICE principle. In short, it stands for Ice, Controls, and Emergence. Let me explain. Ice. Although permafrost is often defined by its thermal state, in the end, what sets permafrost research apart from other geoscience disciplines is that it is concerned with the amount and distribution of ice in the ground. Ground ice and the melting of it is a fundamental driver of geomorphic processes, hydrologic connectivity, biogeochemical fluxes, and ecosystem functioning, and how they change. Therefore, permafrost classification should focus on distinguishing areas with different ground ice conditions. But this comes with significant challenges because ground ice can't be observed directly from the surface, but we'll deal with that later. Ground ice stability and variability are governed by interacting atmospheric, surface, and subsurface controls that are linked through complex feedbacks. To make sense of this and to support consistent classification, we should organize controls by domain. And because controls operate at different spatial and temporal scales, we can also organize them in a hierarchy. If we do this, grouping large-scale controls on terrain and nest smaller-scale terrain controls within them, we can build a classification system that mirrors how permafrost landscapes actually function. We classify them by their controlling variables, and that creates a logical traceable structure for both characterization and generalization. And this idea isn't new. Ecology embraced this kind of hierarchical thinking already back in the 70s. But given how integrated permafrost science is, building on geology, hydrology, ecology, and beyond, adopting some of those same practices is very useful. And then E stands for emergence. What I mean by this is that we can use emergent landform patterns, like ice wedge polygons, peat plateaus, and thermokarst basins, because they reflect permafrost state at the scale they form. These patterns arise as a result from glacial and geological legacies interacting with processes like freeze-thaw, drainage, vegetation growth, and they co-evolve with ecosystems over time. Because they're shaped by both physical and ecological drivers and are observable, they give us a strong basis for mapping and interpreting permafrost terrain. In short, we read the surface patterns to understand landscape function and subsurface conditions. With these principles and an understanding of what's missing in current permafrost science, we've built a structured classification framework. It's organized into 4 hierarchical levels, 3 of which form the core of the system. At the broadest scale, in the top right, we define permafrost zones, regions where climate, geology, and glacial history set the stage for different types of ground ice and permafrost conditions. Zooming in, we have land systems. Surficial geology and glacial legacy give rise to distinct emergent landform assemblages that have co-evolved with ecosystems and reflect current ground ice and thermal states, as well as their likely evolution under warming. These can be broken down into functional terrain units, terrain classes defined by terrain position, drainage, and surface properties. These units help us identify areas that behave similarly in terms of permafrost dynamics, and they're ideal for stratifying sampling locations or constraining models. Finally, at the local level, we have terrain sites as well as plot scale features like individual polygons. This is where field data is often collected, and it's where the fine-scale heterogeneity lives. I hear you think, so what is new? We have been doing classification since forever. And this is true. But what matters here is that this new framework organizes knowledge and nests terrain classes based on the dominant controls that shape permafrost conditions across scales. By following a clear, consistent logic, it offers a more interpretable and process-informed structure than many traditional classifications. Because each level inherits properties from the one above, we can infer subsurface conditions and process relevance in a more structured way. And if we all use this shared rationale, we can make permafrost data and insights much more comparable, transferable, and useful across regions, disciplines, and data sets. Now let's walk through how we actually build these classes, starting at the continental scale. At this level, we ask, what really drives differences in permafrost conditions across Canada? First, physiography and structural geology. These determine where we find deep overburden, shallow veneers, or exposed bedrock, like in the mountains versus lowlands. Then, glacial history. It left behind buried ice in some regions, while others were scoured clean, shaping how ground ice formed. Mean annual air temperature is still one of the best indicators of permafrost extent and persistence that is relatively easy to assess at a continental scale. And finally, winter snowpack. Thicker snow insulates the ground and can be the difference between permafrost persisting or thawing, especially in warmer regions. By combining just these key controls, we create a continent-wide classification that's both easy to interpret and tightly focused on what matters most for permafrost conditions. Now let's move to the next level in the hierarchy. Zooming into the Western Canadian Arctic, land systems become a useful tool to spatially constrain distinct permafrost environments. But first, we need to classify them. I did this using an amazing data set, the Thermokarst Mapping Collective database, that maps out thermokarst and periglacial landforms throughout the Northwest Territories, Canada, at an intermediate resolution. This figure is from the paper led by Dr. Coquel, explaining how the database was compiled, using a grid-based approach to inventory landform occurrences across a vast area. Using spatially constrained hierarchical clustering, I classified grid-based terrain into land systems, each representing a characteristic set of permafrost-related functions, surface processes, and subsurface states. This is what the result looks like. It is still a work in progress, but what's exciting is that, with just unsupervised clustering and the TMC landform data, we've identified land systems in areas already recognized for their distinct permafrost conditions. But these regions are rarely delineated in a uniform data-driven way. By clustering recurring landform assemblages, the algorithm picked up systems that reflect glacial legacy, surficial geology, and ecological co-evolution. From left to right, we can see the northern Peel Plateau, parts of the Tuktoyaktuk coastal plain, and the Jesse Moraine. Looking at the bar graphs, each of these three land systems shows a distinct but consistent landform fingerprint, suggesting shared origins but potentially different evolutionary trajectories. Now that we have contextualized permafrost zones and land systems, functional terrain units are next in the hierarchy. This is really the workhorse level of the classification framework. They're defined by the key environmental drivers of ground ice formation, thermal state, and permafrost persistence at this scale. Things like wetness, vegetation, topographic position, and solar exposure. Because we already know from higher levels what kind of climate, geology, and glacial history we're working in, we don't need to reclassify that. We inherit it. Instead, we can fine-tune our classification to distinguish relevant functional patterns within specific areas. Here's a simple example using the picture in the background. We see what looks like a floodplain and a slightly higher elevation, better drained area where ice wedge troughs are visible. Intuitively, this is how I would classify these two terrain units. To classify these meaningfully using data, we use just the observable controls on ground ice and thermal state we need to tell them apart, like wetness, vegetation growth, and relative elevation. We can use things like the Topographic Wetness Index, NDVI and TPI or geomorphons as proxies for these controls. Interpretability is key. The fewer indicators needed to reliably differentiate permafrost conditions, the better. Now also imagine having classified terrain using these indicators and combining that with information from the hierarchy, as well as from other places where ground observations were available. It would give you a pretty good way to estimate, for example, the probability of finding ice wedges and perhaps even their abundance. So using basic proxies that represent what we know to be controls of permafrost variability, We can divide the terrain into functional units. I did this for a number of places within the land systems I talked about earlier. I picked indices like Topographic Wetness Index, NDVI for vegetation, geomorphons which tell you hill slopes from valleys, and ridges from local hollows, and potential incoming solar radiation. These indices represent controls on ground ice and permafrost conditions, warm versus cold, wet versus dry, vegetated versus bare. This results in a useful and interpretable set of terrain units that can be used to stratify sampling, constrain variability in data, or parameterize models, and that are grounded in a broader context based on overarching classification levels. So the functional terrain unit level gives us a handle on how the terrain behaves and how that could change under warming. Finally, the next level down is the field site. Field scale features like frost boils or polygon rims are scientifically fascinating and ecologically important, but they're extremely context dependent. There are simply too many details that could be worth classifying, and this is best left to the expert in the field. So rather than trying to capture every possible feature of interest in our classification framework, we treat the site level as a flexible, site-defined scale that nests within the functional terrain units. That way, field studies can feed into the bigger picture while maintaining flexibility for researchers to follow their site-specific protocols. By adopting a shared overarching framework, it is however likely that field practices will converge too, leading to better interpretability of permafrost research. Summarizing, I proposed a framework consisting of 3 main levels of classification, while acknowledging that the 4th, field level, is in many ways the foundation to all of our permafrost science. But I have left the field level out of this slide, because being prescriptive about how to do things in the field is not the main focus of my work. Rather, I would like field scientists to adopt and adapt this framework to inform site selection and to allow for their results to feed into synthesis products and models. The levels of classification of the framework I presented are L1, permafrost zones, broad-scale patterns shaped by climate, glaciation, and geology, enabling generalization across regions and contextualizing lower levels. L2, land systems, physiographic settings defined by surficial deposits and glacial legacy, giving rise to landform assemblages co-evolving with ecosystems, providing context for formulating and applying knowledge. L3, functional terrain units with shared thermal, hydrological, and ecological function, forming the core scale for modeling, mapping, and monitoring. Together, these levels form a nested system that enables us to trace how broad-scale controls, such as climate, geology, and glaciation, shape local terrain structure and function, and how local terrain processes, in turn, translate into broader landscape dynamics and climate feedbacks. This is more than a classification. It's a scaffold for unifying permafrost research and guiding where and how we monitor, model, and respond to change. So what is next? A good next step is to apply the framework across disciplines. It is my plan to do this with examples from hydrology and biogeochemistry. Then we should stratify field and remote sensing data by terrain unit, so observations become more comparable and meaningful. This will help parameterize models with terrain-relevant inputs, like soil moisture, ground ice, and energy balance. From there, with data feeding back into stratified databases, we can move toward probabilistic predictions of conditions across unmeasured regions, as well as feeding models to predict future behavior and synthesizing current knowledge. And as more data and regional insights come in, it would be valuable to refine and adapt the framework, keeping it useful and grounded. All of this will be strongest if we co-develop it, with researchers, partners, and decision-makers working together. To sum it up, classification isn't just labeling. It's a way of thinking about processes, functions, and change, and it is an extremely valuable tool for understanding the world around us. Yet, its true power comes to play when scientists use classification following a shared framework. This new permafrost terrain classification framework is going to help us make sense of permafrost landscapes in transition by connecting what we see on the ground to how the system behaves and how it may respond to future climate forcing. For now, I would like to leave it at that and ask you, what would it take for this framework to be useful in your permafrost modeling, mapping, or monitoring workflows? Thank you for watching, and feel free to reach out to me. This work is informed in part by an earlier incomplete effort to synthesize permafrost change in Canada, initiated in 2018. As this work progresses, we intend to connect with key contributors to build on that foundation